My name's McCarter. I'm proud to have been with Liberty for the last 12 years, I reckon, working across a number of different engineering teams, largely in the area of cloud development and, no surprise to you, serverless architecture. I'm a pioneer of office slipperware. I didn't bring my slippers today, so I had to kick off the shoes because I'm a big believer in being relaxed and comfortable when I'm working. And outside of work, I'm a father of 3, 8, 6, and my youngest turns 3 tomorrow. Today we're going to talk about our experience of building serverless architectures at scale. If you're thinking, oh, the shuttle bus starts to sound interesting now, everything I'm going to share, the lessons we've learned, the principles we're going to talk about, are not exclusive to running scaled architectures, but I believe if we are, it is essential. We'll talk a little bit about my story. We're going to talk about how you need to understand the limits and the constraints within which you're working. We're going to talk about being able to observe as you scale, and then finally, how you can scale reliably. So a bit of the background. Liberty IT, as Gareth has already introduced us, we're over 650 people across our Belfast and Dublin offices working into Liberty Mutual Insurance Group, large global insurer. You'll see a whole list of our accolades on the screen, particularly proud of our 2 AWS heroes and our 4 community builders, again, testament to our focus on cloud development. Myself, I worked for many years with our global finance team. We're working with our country operations around the world. We were taking their financial transactions from their core systems of records, and we were responsible for mapping, transforming, doing calculations and aggregations on those, and delivering those to our internal core finance systems, things like our general ledgers. We did this using a serverless architecture on AWS. Peeling back the covers a bit, this is what our architecture looked like, the types of services we were using. I'll step out of the way. If you saw the recent announcement end of last year for the distributed map and step functions, this is a distributed map built around step functions. I believe we might have given some inspiration to AWS. You're very welcome for the new service. Top middle, we've got our job queue where we were queuing up transactions to be processed. Bottom left is our transaction database where we held transaction state. In the center then, the transformation box is where the majority of our work happened. That's the part that ran at huge scale, where we did all the ATIONs, the calculations, the transformations, the mappings, everything we needed to do. And then on the right here, we've got a process that was responsible for gathering all the transactions back again, building that result set that we sent downstream to our ledger. So what's the nature of our workloads? While we designed our system to be able to work with real-time transaction loads, the constraints of our source systems, of our destination systems, Liberty's a big company, meant that a lot of our workloads were batch-based. And so we had country operations sending us batches of transactions, sometimes daily, sometimes monthly, ranging from hundreds of thousands to tens of millions of transactions in a batch. Because it was batch-based, then a lot of our traffic looked like this. We had very quiet periods where nothing was happening, then these huge bursts of activity, executing up to 10,000 step functions per minute, each lasting 10 to 15 seconds, maybe running between 10 and 20 Lambda functions to do all the work that needed to be done. At that then, we were running about 3,000 concurrent Lambdas when we were running at peak. During our development phase, we actually were running as high as 10,000 concurrent Lambdas, but a bit of clever re-architecting managed to bring it down to a more manageable rate. Sometimes more concurrency is not a good thing. So that's the background to our story. The first thing that we learned is you need to know an awful lot. You need to be very familiar with a lot of things. First, you need to be familiar with the characteristics of the system you're building. What's the functional and non-functional requirements you're designing for? That could be things like a transactional throughput. It could be the response time back to your customers. It could be things like your data residency rules. You need to know the services you're picking, why you're picking them, and then the outcomes you're looking to get from them. Once you understand the services you want to use, you need to be intimately familiar with the documentation. We found as we were building, we used step functions a lot. Early on in our development cycle, we were introduced an early preview of the new Express workflows. It was new at the time. It's been out for a few years now. In that, then, we read the documentation. It was very important for us. We almost missed it to pick up on 3 important words. It says when you run Express workflow, it will run at least once. 3 words in a paragraph of text, very easy to miss, but it has huge implications for how you build and how you use that service. You need to read the documentation carefully. Anytime we reached out to AWS support and we asked them a question, they were always able to point us back to the docs that showed us where we should have discovered the thing that we wanted that question answered for. You just got to read it carefully enough. And finally, you've got to be familiar with the workload patterns for your system. I've already described ours, short, spiky, intense bursts of activity. Yours may be a lot more regular through the working day, through a week. You may have seasonal patterns where you get busy periods and quiet periods, but you've got to understand the peaks and the troughs of the workload that you're designing for and what it is you need it to do. Once you understand what you need to build, you've got to understand the environment you're going to run it in. Our AWS accounts have got hard and soft limits. Hard limits are things you can't change. These are constraints you have to work within. A few of them are listed here. These are not all of them. There's soft limits, and these are things that you can adjust. You can go to the AWS support team and ask them if you're hitting against some of these limits in terms of your scale. You can ask them to increase those. Do expect, however, the support team to come back and ask you about your use case. And they want to make sure you're getting the best out of the services that you're using and that you're using them appropriately. The other thing you've got to be aware of is that different AWS regions are different sizes. They scale differently. US East 1, for example, the Lambda burst capacity is 3,000. US East 2, it's only 500. So that can have a high implication on your runtime. If you're planning to pick a second account for high availability or for DR requirements, you need to know if your workload will run in that account based on the limits that are available there. The other thing you got to know is that you sometimes need to be a good neighbor. We were lucky. We managed to wrangle our own AWS account to run our service in. Not every company does that. You may have other applications, other teams running stuff in your account, and you need to share. You need to play nice. You don't want to make enemies by hogging all the resources and causing them issues. This is probably the most important thing I'm going to say. I'll say it very carefully. Increasing the performance of your system increases your ability to incur cost. Now, pick those words very carefully. It does not make your system more expensive. It allows you to incur that expense an awful lot faster, though. If you imagine in a serverless architecture, you're paying for every read and write to a data store, you're paying for the events you trigger, you're paying for the duration of lambdas at a particular level of memory. It doesn't matter if I run a single threaded system for a whole day, or if I pack that all into a very concurrent 1 minute, I'm running the same operations, I'll pay roughly the same amount of money. But the more you allow your system to scale, the more you're going to be able to incur cost. Back to my story, we were running large book close processing end of every month. Our business wanted the confidence that our system could handle their volumes, could scale up fast enough, would process things quickly enough, and that when we put $10 million in one side, they got $10 million out the other side. And so they did what they love to do. They set about testing. Within a matter of days, we had tested a full year's worth of financial transactions, and that came within a full year's worth of billing. We had some very interesting conversations. It's very important that we educate our engineers, our test teams, and our business teams about the nature of these workloads. Very important that we have testing strategies, that we stop and think, how are we going to test these? When is it appropriate to run a full volume test? And when actually can we get the same outcomes and the same results running a much lower volume? So we understand the constraints of our system. We know what we want to build. We can draw it all on a whiteboard. But I'd argue at this point, you still don't know if the system you've designed is going to scale well. There's too many variables at play for you to accurately predict that. I don't know how long my Lambda function is going to run for. I don't know how many shards are going to be in my Kinesis stream that's going to kick off the Lambda. I don't know what the concurrency at Lambda is going to end up being because Amazon controls that based on all those factors. And then I don't know what knock-on effect that has to the next process and to the next process and so forth. And so to know how our application is going to scale, we need to start doing experiments, we need to start building POCs, making hypotheses and trying them out. It reminds me of generative AI, hard word to say, got it out. You give it a very clear input, be very descriptive of what you want it to do, but until you hit generate, until you see what's happening, you don't know what it's going to create. So here's my Iron Throne, take the Game of Thrones reference. And so you need to run your system, and then you need to be able to observe it. You need to understand the metrics that are attached to the services that you're using. These are a few of the metrics we use for some of the services we were using. These may not be the services you're using, the metrics you want to use, but you need to be aware of what these metrics are and what they mean to you. As you grow your architecture, you're not going to be able to put every metric you care about onto a single dashboard, and you definitely want to be paying somebody to be sitting all day looking at it either. So you've got to start to understand, what does a normal workload look like? What's the normal working conditions of my system? And therefore, what are abnormal working conditions? What alarms and thresholds do I want to set so that I know when things aren't healthy? The ideal state here is that if you've got a Lambda function, for example, that's running 10% longer week over week over week, that you can get the alert for that. You can troubleshoot that, debug it, and deploy a fix before it's causing you production outages. And then when the alerts come through, when the alarms happen, your engineers need to know how to respond to those appropriately. We need to understand how all of our services hang together. We may see multiple signals appearing on our dashboards. We need to be able to put the pieces all together to understand, if I'm seeing this here and that here, that tells me what's going on. I mean, a Lambda duration increasing, I know what's happening. The Lambda's running longer. I don't know why. I need to know how to troubleshoot that. That could be through my logging, could be through more dashboards. I could actually just sit and looking down, what does that Lambda talk to? The picture on the screen is a much more complicated dashboard, a much more critical system. You may recognize it if you watch any of the docu-series. This is the reactor, the control room at the Chernobyl reactor. My layman's understanding of the situation was that the engineers in the room didn't understand the system that they were monitoring. And so they didn't understand, when they saw the signals from the dashboards or from the readings they were taking, how to make the right decisions in order to avoid failure. I'm not saying we're going to have a nuclear meltdown on our hands, but it's a nice illustration to me in terms of how we need to understand what to do with the data that we're seeing. And that brings me on to how we need to scale reliably. The one certainty I can give you is that things will fail. Amazon has a really good commitment around the uptime and availability of the services that they provide. But when you start to scale your systems and you're running millions upon millions of things, anything that is a may becomes a will. If it may fail, it will fail. If it may run more than once, it will run more than once, and you need to be able to allow for that. I'm not telling you we were seeing 500 Lambda errors every minute, but we were seeing errors, a constant buzz in the background, and your architecture needs to be designed to be able to cope with that. So how do you do that? Chintan already mentioned it earlier. You need idempotency. You need the ability to be able to retry your operations with confidence. Idempotency is that ability to rerun an operation or function over and over again and not have any negative or unintended side effects. My very crude sequence diagram on the right here shows an orchestration layer calling the function. It's got some output signal. The output signal starts at 1. When I call a function, it says add 1. But for some reason, maybe it's a network issue, the response doesn't come back. And so the orchestration layer says we need to retry this. And it retries, it says add 1 again. But because my function is idempotent, the output remains at 2. Get a successful response, and the whole system's now correct and complete. For us, achieving idempotency involved tracing an awful lot of transaction IDs and monitoring which transactions have been through which parts of our calculations. For other teams, that might be deduping events downstream of your architecture. I could be using calculated IDs to do upserts into your database. It doesn't matter how many times you insert the same row of data, it's still there in the same place. You need to figure out for your architecture how you're going to allow for that ability to retry. I mentioned before, we use step functions. Step functions provides really good capabilities around catching errors, around responding to errors, controlling how many times you retry, when you fail back to other options. And so just back to our architecture. As I was describing, we were a financially significant application. We were managing the financial reporting for a Fortune 75 company. We had 0 tolerance for error. I couldn't process somebody's premium twice or double book their claims payment. But through an awful lot of learning, an awful lot of difficult experiences, we understood the constraints of the services we were using and the environment in which we were running it. We learned how to observe the system as it ran and how, when things didn't work the way we expected, to debug and troubleshoot that. And finally, we understood how we had to design for idempotency to allow us to do retries, to allow us to achieve the reliability we needed to fulfill our business needs. And that's all I have to share with you today. Thank you for listening. And if you want to catch up before we all run to the shuttle bus, I'll be hanging around. Thank you very much.